Saul or
Yeah,
Paul? Saul. Okay.
No, Saul, sorry.
Because both are presenting today, so.
Yeah.
okay. I don't know if I am allowed to share.
You should be.
Let me see. Okay. I'm having problems with my computer. Give me a second, please.
Okay, sure. No worries.
Okay, I need to to restart my Zoom, so I'll be back.
Okay. So,
Sorry.
It's okay.
Okay.
So what should we do? So let me go ahead.
Okay, so today I'm going to present this paper, which is most related with, let's say, benchmarks and some comparisons between the four most famous platforms for for serverless computing. So before start, I want to provide us some context about what is serverless. So I found this the definition from IBM, which I think it fits perfectly for our purposes. So I'm going to read. And for IBM, serverless is focused on any service category, either computing or computation, storage, database, messaging, or API gateways. And these services are managed and are billing, or the billing it's invisible to the users. So when the first time when I'm honest, the first time when I heard serverless, I thought that it was how I'm going to develop an application without serverless, right? But in this case, this definition it's quite sure because it says that the billing and the management it's transparent for the user. So we are not aware about the management. We are not aware about the servers. We are not aware about the operating system. We are not aware of nothing. We are only required to focus on our applications, to develop, and that's it. So related with this serverless, there's a new concept, which is FaaS, function as a service. And this is what we will be evaluating in this document. This paradigm or this service, this kind of service is related with serverless. Serverless is not only FaaS, the function as a service. As I said, serverless it's more than computation. It also has the other concepts, but this FaaS is especially important because this is the kind of service that this paper discusses. So in the paper, we talk about, or these four platforms are tested. So these are the four. I think they are the most popular. There are another cloud providers with functions, but they are not quite famous. So in this paper, we're going to measure the performance of Azure, IBM Cloud Functions, the AWS Lambda, and Google Cloud Functions. So in this paper, there are 10 concepts for the evaluation of these platforms. We are going to talk about in detail about all of this, but this is in general the evaluations that performs that are performed in the paper. I want to make a point here because this paper is from July 2018. So please don't be don't scream if some of the data of the information presented here is not quite exactly because this information it's very old. There have been 4 years, but yeah, in our days, even 6 months, 3 months is a trip to the future. So just please keep that in mind, that the information presented here is from 2018. And the first concept that we of the first metric is the function throughput. A throughput is a measure that the systems performs to process informations. So for the first evaluations, the authors of the paper create 1,000 functions with identical logic but different name. So this was to simulate that a function was called in parallel. So these 1,000 functions will be considered as a one function also, or as a one execution for these evaluations. So we have a table with the results. So some things that we can see here, it's that well, the first line is because the authors perform 500 invocations up to 10,000 invocations. So I'm just in that line, it's just marking the 500 invocations. So one of the most important things here is that, for example, for Lambda, Lambda reached its maximum capacity with 1,000 invocations. So its maximum capacity is reaches almost like 3,000 function invocations. But since 1,000 invocations, we have almost its maximum capacity. Another thing to see is that, for example, IBM reached its maximum capacity with 2,000 invocations. Google, we can see that it has like a linear curve that says that as long as you request or perform function requests to Google, they increase the throughput. And another thing that we can see here is that, for example, for Azure, they have a little weird behavior, because with 500 invocations, let's say 1,000 invocations, the throughput it's decrease. It decreases and then it starts to increase. So the next evaluation for this paper is concurrency in the CPU, and the way that they make this evaluation is with a JavaScript functions, and that JavaScript function includes an array multiplications, and we know that the arrays always require a lot of processing, and in the same way there were one invocation and 100 concurrent invocations. So in these results, we can see that, for example, for Amazon, for one invocation, there are 19.63. In this case, the measure is in gigaflops. So for one execution, the Amazon environment could achieve 19.63 gigaflops of performance. And we can see that Azure, Google, and IBM has the lowest values, either for one function execution and 3,000 execution. But this is because at that time of this paper was written, those services were in the beta mode. So that's why they have the lowest values. We have a graphics here about the performance. And the first thing that I want to mention here is that in the x-axis, which is the time, we can see that Azure takes so much time to finish the execution because it takes 400 seconds. Google also takes a lot of time with 40, almost 15 seconds. Apart from that, IBM and Amazon have the lowest time to finish the execution. So in the case of Azure, for example, the dashed line, which is the execution for one invocation. Since the graphic shows a big time, we are not quite sure about what is exactly the time that takes for Azure to perform one execution. It seems like it is like a vertical line, but since the graphic it's scale, we cannot say what is exactly the performance for that. So another evaluation made for these platforms was the concurrency for the concurrency for this. And in this case, the configurations were the users create, the authors create a function that writes and reads information from a file. The writing file was 100 megabyte size, and the read was with an offset block of 5 and 12 bytes. And about the storage, there are no information about what is the infrastructure that Google, Amazon, IBM on Azure has. We don't. The authors don't know if their storage is a solid disk or if it is a traditional disk. So in the left side, we have the median speed for write and read for one invocation. So in this case, we can see that Amazon has quite a good performance for write and read, but Azure for one concurrency or for one call for reading, it's a beast. So they can read a lot of information. Google and IBM, well, they read very well, but the writing it's not their things. In the right side for the graphic, which shows 100 concurrent invocations, unfortunately, Azure at the time was unable to support 100 executions because of storage space issue. Maybe it's because they were in their early stages. But in the same way, we can see that, of course, the performance gets slow. But yeah, we need to understand that they are 100 concurrent invocations. But yeah, IBM in writing with 0.5 megabytes per second. Yeah, I think it's very, very bad. Amazon keeps a good performance. Yeah, considering the amount of invocation, they are still keeps a good performance. So yeah, Azure has the most competitive speed. And for example, for the 100 invocations, Amazon is 11 times faster than Google and 78 times faster than IBM in writing. So we can see some of the overheads, which is a measure of the resources that we require to perform the task. And we can see that IBM has a lot of overhead or has a huge amount of overhead. And we can see the graphic. It takes 16 seconds to finish the task to be able to process 100 invocations. And as we can see the graphic, it seems like for almost 20-30 seconds, the processing the invocations takes a lot of time. So despite of maybe 15-55 seconds, it starts to the overhead increasing. And another evaluation was the network in the servers. So in this case, it was a simple call, a function that requests 100 megabytes of data. That's it. And were made 100 invocations that in total were 10 gigabytes or invocations. So let's say for each provider, the function requests 10 gigabytes of information. So in this case, we can see that, for example, Amazon and Google, Amazon is 4 times faster. And we can see because Google takes 10 seconds to process all the 100 invocations, and Amazon just takes 2.5, almost 3 seconds to accomplish the same task. For Azure, we can see that it's unable to accomplish the task, and the author says that maybe it's because they were in an experimental runtime. And I want to remind, this is from 2018, so maybe they were experimenting with their runtimes. And at the same time, we can see that IBM takes a lot of time to finish the task, maybe almost 16 seconds. But it takes a lot of time, but they finish the task. Another concept here is elasticity, and this is related with how many new instances are instantiated when user requests a lot of requests. So in this case, the authors create a function that were able to finish in less than 100 milliseconds. Each function was executed between 10 times and 90 times. And in total were 10,000 invocations in a period of time of 60 seconds. And they use Node.js full-time. So the function was written in Node.js. This is a quite complex graphic because it shows a lot of information. But let's make some clears about this. So in the x-axis, we have the invocations that it's from 0 to 10,000 invocations. So in the y-axis, from the left side, we have the invocations that was from 10 to 90. And in the right side, in another y-axis, we have the execution time. But for example, let me see if I can. I can annotate. Yep. So for example, let's say, in the gray line shows the invocations that were made during these 10,000 invocations. So for example, the invocations goes from 10 to 90. So let's say we have, at this point, we have 15 invocations, and these 15 invocations takes almost 120 seconds to finish at this point. So now, the blue dots, it's the execution time. So for example, these 15 invocations, I don't see the dot, but maybe let's say it's from here. So it took almost 90 seconds to finish 15 invocations. Let's say this point, let's say it's 30 invocations that took almost 110 seconds. So in this case, we can see that, for example, another thing that I forgot to mention is the yellow and the green line. For example, for the most important is the green yellow, because for example, for Amazon, the green yellow, it's it's near to 10 milliseconds. So that means that 99% of the invocations were finished in this case in 89 milliseconds. So for Google Clouds, the 99% of the invocations were finished in almost 2000 milliseconds. For IBM, 99% of the invocations were finished before 400 milliseconds. And the worst was Azure, because 99% of the invocations were finished in almost 3.2 seconds. So this is basically what this graphic shows. And for this case, for Amazon, according to the authors, 54 instances were created, Azure 10 instances, Google 101 instances, and IBM 100 instances. So it's curious because Google almost has the double of instances that Amazon. And yeah, Google finishes in the double time that Amazon. So maybe they require the double performance that Amazon needs. Another concept that was evaluated was the continuous deployment and integrations, which in short words, it's DevOps. So in this case, it was an interesting test. The authors create a Node.js function with a total of 500 executions. The first 100 executions were created with initial functions. Then they changed the function. They changed the source code before complete the first 200 invocations, and after that they changed completely the function. So they change calls to the memory allocations, to database calls. They change completely the logic of the function. So in this case, we can see the graphic, and for example, the gray dots represents the instances that exist since the beginning of the application. The green ones represents the new instances created during this test, and the red ones represents the failed instances. So in this case, we can see for Amazon, according to the authors, it seems that they redeploy the applications because we can see these two lines. And maybe this is because the function was being executed, they changed the code, and all the new function is instantiated in these new instances. They manage the new request, and when they made the second change of code, yeah, it seems that all the new instances are created. Okay, Google, it's create new instances in this period of time, and we can see that a lot of instances failed. For IBM, the authors say that when the first 2000 functions are executed, it seems that they just stay on hold until new instances are requested. So that's why at the end of the graphic, we have a lot of green instances and less gray instances. And Azure, in the other side, has less instances created. So it seems that Azure performs very well the management of the DevOps. That means the code changes.
But just one question.
Yep.
In the previous slide, it's also important that time, right?
The time, it's not important.
Because in the AWS, it took just like 4 seconds. And for Azure, it's 40 seconds. I think the performance is, well, 10 times.
Yeah, but in this case, what the authors are evaluating is how the providers manage these, let's say, code replacements. So in this case, it's more related with how new instances are, if they are created, if they are update the version of the function that they are running. That's why for Azure, despite it takes a lot of time to execute the task, but they create less instances. So it seems that an instance is running a version of the function. The user requests a change on the code, and the same instance manage the new request with the previous version of the function and with the new version of the function, and continues working. So that is more related for the authors. Yeah, the time is important, but in this case, I think it's for the instances.
Okay.
Yeah, the next evaluation was the serverless, which is the topic of the of the paper, versus the traditional virtual machine. So in this case, the authors create two scripts, one written in Python and another written in JavaScript. And the author just provide this table, and they only compare the costs between the function service or the fast service between the traditional virtual machine service. So, for instance, Google in their in their virtual machine service, they have the best performance according to the cost. They have the lowest cost, followed by IBM, and at the end Amazon. But yeah, with the traditional virtual machine service. So we can see that the fast service, it's still not quite good according to this table, but according a lot of information on internet, and there's a IBM video that I saw which compares the billing. So in this case, the traditional virtual machine servers, they bill from hours or minutes, and the fast service bills for seconds, or let's say milliseconds. So another concept was triggers. In this case, three triggers were executed: HTTP, a database, and object storage, with 3,000 concurrent invocations. So in this case, we can see that for Amazon, Amazon is able to perform the three triggers. Unfortunately, Azure, Google, and IBM doesn't have a. So for example, for Azure and Google, they don't have a direct trigger for their database. In IBM, they don't have a trigger for the object storage. So, for instance, we can see the results. For Amazon, the gray chart, it's broken because the scale of the table. So they jump from 250 until 800. But yeah, these are the results. Not much information, just the triggers. And one of the last characteristics evaluated was the features. In the same sense, the authors only provides this table. The information may be not quite well, it's not updated with our current with the current versions from today's. But with the table, we can see that, for example, Amazon at the time has 18 triggers. The author said that IBM doesn't charge for a fast execution. In other words, if you want to execute a fast function, Amazon, Azure, and Google, they charge or they make a bill when you execute that function, but IBM not. Something weird in the paper, they say that Google has the best execution timeout with 9 minutes, but in the table, you can see that Azure has 10 minutes. So I don't know why the author said that Google has the advantage with 9 minutes when Azure has 1 minute more for the timeout. So the last thing is the language support. And at the time, this is a very tiny table for the providers. So we can see that, for example, Google only has Python and Node.js. Amazon has the most, Amazon with Azure, they have the most language support. But just to make a comparison with nowadays data, this is a comparison with IBM runtimes, and we can see that they now include Swift, PHP, Go, Ruby, and they now support the .NET platform. So these were the 10 evaluations that made the authors. I think it's a little unfair to discuss this today because they are very old. The information is not quite accurate. But yeah, I think these kind of evaluations may be performed periodically, let's say at least 2 years. So the companies, the enterprises can see a comparison between all the providers. So I think that's it. So if you have any questions, comments, please go ahead.
Okay, thank you, Sol, for great presentation. So let's have a question answer section. Who is leading the discussion? I don't remember. So we have Juan here.
Hello.
Yeah, we can hear you.
Yeah, this topic, evaluation of production serverless computing environments. Hold on. I think I have a problem here. Okay, we already know that we have to test all the systems with invoking functions in parallel in order to know the performance, analyze bottlenecks, and to see which the behavior. So do you have anything that we can moving on with the performance about this about the systems?
I mean, first we can see if anyone has any question about the paper. I mean, about the presentation, about the paper, about the results.
Yeah. So do you have any questions about it?
I don't see any question by anyone. So I would just like to see, I mean, for something like you did, Saul, for the last presentation, I know the paper was from 2018, and as you mentioned, really, I mean, the technology is changing so fast, so maybe 4 years is too much time to rely on. But I mean, it would be great if you could, like exactly like last slide that you put, it would be great if you could
Yep.
do that, like that comparison for not for everything, at least for some of the results. But I don't know, like, is there anyone here that knows any changes, like anything that changed massively, like I mean, comparing all these 4 companies?
I have a question.
Go ahead.
Yep.
What are the biggest advances compared to when the paper was published?
What was the
Sorry.
question?
Yep.
Yeah, well, related to technology was not like the best a few years ago. Well, I haven't used these tools, but what are the biggest advances compared to when the paper was published?
I think one very big change, something that has really transformed the way we use these functions are custom runtimes. So basically, right now we see support for all these languages. However, this is support of it being used natively in their platform, in that you can see the code right there and being executed. However, as of right now, many of these have custom runtimes. You just simply take whatever it is working for you in whatever language and just adapt it into a container, provide an entry point, provide a way to say this is the output, and you're good to go. So right now, basically all of the runtimes are supported. The only thing is that you can't actually see them play right there. They are executed, but they don't have like all the nice functionalities of you actually doing debugging in the console. But yeah, I mean that changed a lot of things because in the past it was like you were like Python developer or JavaScript developer, you were like, okay, you can go on Lambdas, but right now anyone can go into Lambdas.
Thanks.
Yeah, and actually, in the Amazon documentation, the new dates it has increased very. It has a very increase in the run times, even with the versions. For example, for Java, they support 2 versions of Java 8 and Java 11. For Python, they support 3.7, 3.8, 3.9. For Node.js, they support the 12 and 14 and 16 version. So yeah, they are increasing their support. And yes, Rodrigo said, you can customize or you can code in whatever runtime or language you want.
Okay, I have another question. In the comparison between serverless and VM, well, it seems that VM is the best option instead of serverless, right?
Yeah, but I
Do
think
you
yeah,
think
go ahead.
that has changed today?
I think it depends on what are your necessities.
That one. It seems
Yeah.
like VM is better, at least in this case. It seems that it's better to choose a VM instead of the serverless option. Do you think that has changed right now in the future or in the present?
Yeah, I'm quite sure that information have changes for today's, but yeah, I think it still depends on what your application or your company is looking for. So, for example, for the virtual machines, and the cost is for minutes or maybe hours. because it doesn't matter if your virtual machine is turned off. You maybe still be charged for the use. So the benefits of the fast function is because you are only paid for what you are using. But at the same time, I think they both of them are created for different purposes. So it totally depends on what are your needs.
Okay.
But why you're saying that virtual machine is better? I mean, what number you're saying and referring to?
Yeah, that's for a cost price, right? Only this table.
Yes.
Yeah, because it's like if you want to save money, probably yes, but either way, the execution time and things like that are different on each one, right? We saw
Mhm.
before.
Yeah, that's what we
Yes.
see in the other paper, right? In the second one. That it says even when, yeah, maybe it's cheaper to use a VM. There are a lot of things that you are not saying, like all the stuff that you are, all the time that you are going to say, because you are not doing nothing related to the elasticity that is done automatically by the provider. Okay.
Yeah, this table is only for for cost, total cost, and I'm quite sure that the information displayed here, it's not all not all the concepts.
Yeah, I mean, and also you can, maybe you can pull it up and get like a cheaper deal at the end of the day. But I mean, theoretically, you would need less people to manage less infrastructure, right? I mean, so in that sense, it would appear as cheaper, but at the end,
Yeah.
I mean, it really isn't, right? So yeah, I mean, that is also taken into consideration. That's where most of the money goes to.
And that's the sad part, right? That's difficult to
Yeah,
calculate.
I mean, that's, and also people get moving, and whenever they move, you need to get them on track again, and then they leave again. So yeah, you're no place.
So anyway, how do you think things changed from last 4 years? I mean, most of the results that you show, most of the comparison, AWS was Lambda was winning, basically performing much better in most of the things. So is there anything changed, you think, or is still AWS? I mean,
I think that AWS has changed something, because I know at least from the course that I'm taking from CDK, it, like, for example, the Lambda functions before, you create like a big image that you were deploying when executing a function. Like, for example, if you wanted to execute a single function, depending in how you package the function, sometimes you package like several functions, sometimes you package only one file, but always, since it's running in a container, the container size is like really heavy, and they have reduced like that heaviness and also the packaging method. So I know that before, let's say, one of the main images, like the footprint of the container, it was like 3 GB, and right now it's like 1 GB. So I don't know if because of that, also the performance has increased, you know?
Also talking about GCP and the cloud functions, like 5 months ago, they launched like the cloud functions second generation, and there are a lot of different improvements talking about concurrency, instance size. For example, talking about the size of the instance, it's like the double. And also talking about the timeout, instead of 9 minutes, right now it's like 1 hour. Talking about the HTTP trigger. Well, also with the concurrent part, right now you can trigger for one function 1,000 requests at the same time. Before that, it was only possible 1 request per function. So probably right now it's very different, the comparison between the different cloud providers. So yeah.
Yeah, I thought that this will be an unfair comparison, since the paper said that for the CPU intensive workload, Azure, Google, and AVM were in beta, in the beta release. So yeah, it is a little unfair to make that comparison.
Also, they should support more triggers, right? Azure, Google, and IBM, they supported very few triggers, right? But probably now the list has increased, right? And it is also interesting that, well, I don't know, sometimes you feel like you're starting a project and you feel a little discouraged that some solution already exists, that, hey, but this solution is already there and it has a very good performance. Why should I care about doing something the same? So I don't know, it is kind of motivating that to try to improve something that already exists. And I see that in the case of Microsoft, Google, and IBM, well, they definitely need to improve their services so that they could take a piece of the cake that Amazon had.
There is a question here for Manuel Herrera. And which is the worst of all? And why is Azure?
Yeah, it was like a little joke, but at the end, it's I don't know. In my experience, it's really hard to use Azure with the I don't remember the app something. I don't remember the name, but at the end, it's really hard. I don't know what
the app service instances, those, or which?
Well, I don't know the name. It's like the cloud function in Azure. It's that.
Oh,
Okay.
Interesting.
So just a quick question from right here. I mean, I know we have people from Oracle. Do you have any like strong opinions on Oracle's cloud proposal or solution?
When I was making the presentation, I went to the Google site, and they are currently introducing their cloud functions. So I didn't know that Oracle has functions, but yeah, they are introducing it.
They are called Oracle functions, actually. I work with some of them. It's so easy to set one functions, and yeah, they support containers, they support Node.js, everything related to Java.
And how about downtime? I mean, do you know everything about like in its SLA, if they say something about availability and how that is compared? I mean, because at the end, AWS and these big providers are supposed to at least have like very high availability, right? Like, I don't know, like 4 nines or whatever. But I don't know about Oracle. Does Oracle already have those many nines, or it's like 3 nines or?
Well, Oracle is growing, so they have a lot of issues related to that stuff, like growing. You know, when they are growing, they have like for example, several times a month they are down in some regions or some areas. So yeah, they work fine, but they are growing and they are learning also.
Okay, so there is any hope one day we see comparison with AWS and Oracle?
Well,
Yeah.
they are putting so much effort on the cloud. I think right now, after the database, the second main point of improvement is the cloud. They are really trying with the cloud. So I think, yeah, maybe in the future they will have something that can compete with AWS.
You guys are not gonna believe it. Just received a message from the Oracle Cloud Infrastructure because there were multiple infrastructure services errors.
Or
They're
other
roaming, I said.
The worst can
Of course, timing, right?
yeah. And Pedro is like, "Shh." He will tell later.
Interesting.
Yeah.
Yeah.
Oh, the shame.
Interesting. Okay. I don't know. Is there any other question or anything want to add? Anything? Anyone wants to add any other things? I mean, the good thing here, I mean, is the way I think they perform their comparison. That's a good way actually to look at it. And I mean, unfortunately, no one was interested here to perform similar results, like updated one. To basically.
My only observation here is why IBM. I didn't know that IBM had a cloud.
No.
Yeah.
Yeah,
Anyone from IBM here?
actually, they use the Apache functions because it's Apache OpenWhisk. So
Yeah,
I
and
Okay.
yeah, and also it's based on Docker that so.
Okay. So thank you, Saul, and everyone participating in this discussion. So we can have like 5 minutes break. We come back 7:40 and we continue with Ricardo presentation, with Rodrigo presentation, and we have Ricardo here. So we come back by 7:40.
Okay.
Just
Thank you.
5 minutes to stretch and drink something. So you can go ahead, Rodrigo, you can share your screen. You are mute.
Yeah, yes, sorry. So can you see the presentation already?
Yes, yes.
Yeah. Okay then. So do I start now or should I wait for?
No, you can start.
Okay then. So hi everyone. This presentation is kind of similar to the last one in that we will be looking at some benchmarking. However, this is, I think the advantage of this paper is that they go like a lot into explaining each one of the tests and also provide like a little more context on which are the nuances of serverless. But it is also a little smaller in the sense that it doesn't examine like so many characteristics. So let's go. And also a very important detail here is that it looks for how these factors are related to microservice performance. So yeah, so a quick recap. Saul just did a better job than me explaining this, so we'll go quickly through it. What is serverless? It's basically automatic provisioning and management of compute infrastructure. And what is function as a service is basically pues, all these custom runtimes in which we don't need to care about any of these parts. And we have, as you know, the Lambda, these cloud functions, these Azure functions, and so on. And yeah, well, just this little image in which we are starting to believe that in the future to which we are going to, we won't be needing servers. I mean, the only thing is that servers are in other places. It's not that they are disappearing. So here we need to start preparing for serverless, right? Things are changing, and so our behaviors and our trends and how we manage our teams. So first, we need to get used to getting all of our applications decomposed so that they can be deployed as independent code modules. And also, we should start now leveraging containers such as Docker and the other like the Linux solutions like LXC and LXCD or something like that. And why? Because, well, containers also help. I mean, at the end, what the providers do on their end is load balance containers across virtual machines, across physical servers. Here's a quick table. I extract this one from a reference that is not from the paper, from the Cloud Guru page that I think Ricardo will also mention in the discussion. So as you can see, each one of them have some advantage in a sense. For example, how many monthly requests they offer, which one is cheaper, which one has greater concurrency, which one has like the smaller cold start, how much memory they offer, the maximum timeout. And at the end is that, I mean, most of the times you end up in any of these providers. If you are the ones taking the decisions, well, good luck with that. But many times you are not. You are just like, okay, we're using this, so just stick with it. And usually we're just like knowing these parameters by hand and not really comparing among like different cloud providers. Well, except for people that I don't know work like setting up the project from the ground up, to which I really have tons of respect because taking these decisions can really lead a project to very different places. So going back to the paper, what is everything about? It's about the factors that influence performance of serverless microservices. And why do we want this? He basically wants to enable better application deployments. So what is a microservice? This was also mentioned by Saul in the last presentation, but for me, it's like better explained when compared to this monolithic architecture, which is the way things were supposed to be done before, in which basically we have all the code either comes from business logic, data access layer, and the user interface in a single place and is deployed as such, as a single module. And it also scales as such, meaning that whenever we wanted like, I mean, you can also scale it like vertically and horizontally, of course, but in many cases, at first you start scaling vertically and horizontally only for load balancing reasons. But at the end, each one of those instances have all the same code. It's not that they have different versions of the code. And then comes the microservice. The microservice, basically you have code that can be deployed independently, and that each one of them can, for example, have access to the database, and for which you have a single user interface, which can be in front like a load balancer, or for example, some discovery service that does know about all of these microservices. But at the end, or even the client, I mean, the client can be doing the load balancing, but at the end, you need someone to know about all of these places. So as I was saying, this is about the factors. So let's talk about these factors, the ones that they are at least proposing. So first, they are asking us, what is the impact of cold versus warm service requests on performance? To understand this, we need to see how Lambda or an Azure function instance really gets created. It all starts in the physical machine, Then the physical machine gets multiple virtual machines. And in one of these virtual machines, multiple containers are set. And in one of these containers, our code comes in. As the infrastructure moves from the physical place, like the metal, into our code being executed in a container, it moves from warm to cold. And this process, I mean, in this sense, is known as provisioning. And in the other sense, is known as deprovisioning. If a request comes in and there was no code at all, then it is in the provider code state. And it needs to wait for all of this to happen before actually getting a response. But it may happen that a request comes in for a Lambda that still has the container on. So it only needs to run the code, or that already has a virtual machine and the image is cached. So it's right around here. So as you expect, it would get a quicker request, I mean, a quicker response from the service if it gets closer to the warm end. Now, the second question is how load balancing impacts microservice performance. Load balancing in microservice is done for us, right? The serverless automatically do it for us. And how does it do it? It can be, in most of the cases, you see it based on CPU load or simply round robin. Round robin is basically you take turns, and when you are gone, you go again and just get into the queue. And whenever it's your turn again, you get a request. It's not that complicated. Also, what is the impact of provisioning variation? This one is a term that is a little more difficult. So basically, when we have many containers in a single virtual machine, there's a possibility that the image gets cached. And if the image gets cached, we get reduced call to launch latency. That goes very related to the cold and warm ends that I was talking about. However, having this increases the possibility of having resource contention. And this, what may happen in this case is that there is a conflict over a shared resource. Now, this conflict is like a little more difficult to explain. It's not really related into like namespaces and C groups, but really into how the physical resources are assigned to each one of the new instances that come up. To better understand this, I took an example from the not so serverless world, that is Kubernetes. Basically, how does Kubernetes work? You say, okay, I want a host that looks like this, that has, I don't know, 2 images, which have certain memory and CPU limits and requests. And there's a scheduler right here that is in charge of finding some host that has enough memory to allocate these images and just set it there. So the pods do have C groups and namespaces to protect, as I say, CPU, RAM, and IOPS, and namespaces to basically protect all the network space. However, the scheduler, that is the one sitting right here in the API server, needs to make sure that the sum of the resource requests of the scheduled containers is less than the capacity of the node, or else it just doesn't place the node, and there's like a capacity check fails. If there was no scheduler, or if someone forgot to state how many memory they should be requesting or limiting or be limited to, then the scheduler, the only thing that it does is that it doesn't have like any quality of services guarantees, takes up whatever node it's around there, whatever pod, and just place the new one in. And that this is like the new resource contention, not like the previous one in which people were like actually getting into the same memory space and corrupting themselves. And last but not least, we have 2 other factors, that is infrastructure retention and memory reservation size. For infrastructure retention, as I told you, containers in one state service this request more quickly. However, we can keep the infrastructure forever in the same place. And therefore, there's some process of infrastructure depreciation, which obviously impacts performance. And for memory reservation size, platforms do allow users to specify a specific memory reservation size, which is applied to containers. However, since this is one of the only few parameters that allows that users can actually control, we usually tend to parameterize it wrongly. So we'll see about that one. Okay, now let's really go into the experiment. So just a quick doubt. Are you hearing me okay with this microphone or should, yeah, okay.
Yeah,
Yeah.
clear.
Very good. Quick. Let's go into the experiment. So I will use the AWS case. They also set a similar scenario for Azure functions. I will not use it because, as Manuel said, we don't like Azure. So let's go with this one. So basically, what did they say? Okay, we will set up a Lambda. This Lambda will just do certain number of calculations using operands from an array. Okay, up to this point, this is very easy. However, we can parameterize the amount of calculations and also the length of the array. Why? Because by parameterizing or customizing the number of operations, we are introducing CPU stress. And by making the array longer, we are introducing memory stress. Or at least that's why they expect what they want to do. And how can we trigger this Lambda? In this case, they set up an HTTP trigger, and they set up a client which was sending like various amounts of requests, specifying the array size and the number of calculations, and getting back from the Lambda the container UID and the virtual machine boot time. How did they get this container UID and virtual machine boot time from a place that doesn't really know where it's running? It's a very interesting discussion that you should really take into account and reading the paper, because I mean, it's a mess. They set up some probabilities and say about like the virtual machine boot time, what is the probability of it spawning so many times in different places for different containers, and then it just checks which is the file that is shared between all of the Docker containers and writes a temporary file there. And then if it finds that file, it can guarantee with certain degree of certainty that is the same container. And yeah, you can just go on and read it. So okay, this is the setup. And then they say, okay, we will set different levels of the stress according to the number of calculations and the size of this array. And they set a stress level from 1 to 9, with 9 being a greater stress. Okay, now let's get this thing running or whatever. First, they did like a base case scenario, and they compared with a basic Docker case. They did like, you can imagine that this is like comparing against server full, okay? And they used a library that is called Docker machine, yeah. Docker machine that basically allows you to trigger and spin up Docker containers on the fly. So they compared this same calculation service with these same parameters with this base case scenario, and found out that they can at least use this test case to make tests. So as you can see here, they set up for the run performance scenario, this Docker machine versus Lambda. This should be 12 threads. They have this one wrong around here. They explained in the paper that is 12. So basically, as you can see, they behave similarly for the warm run performance when they start increasing memory and see what is the average runtime of the service. And for the cold run one, for example, you can see around here that Lambda does take some time to start running, but once it does have certain memory, it can start like behaving very similarly. So this serves them as an example that their test case at least represents accurately and that their stress levels are working. That was like their big, like what they found out with only these cases scenario. And also that Lambda 1's performance is quite good, as you can see around here. Then they first tested elasticity. How did they test elasticity? They started incrementing the number of concurrent runs and started measuring how many containers appeared. And this is very elastic, right? If you get more concurrent runs, then more Docker containers should appear around. However, you don't really know in which hosts they are running. As you can see, hosts kind of sometimes appear to be related to, I mean, as you get more containers, you do get more hosts, but not necessarily, as in this case. And this may happen because a host may have more containers than the others. And also, well, according to the relationship between the host and the containers, you get different amount of runs per host. And what about the runtime? How did it behave in this case? Well, as you can see, as they start increasing the number of concurrent runs, the service starts to get slower and slower. And well, as you can see, there's like this performance degradation. And if you consider, for example, from 10 to 100, it is a performance degradation of 2.6x. So yeah, I mean, it's something significant. That's for elasticity. For load balancing, they tested by increasing the stress level and figuring out how the containers started like assigning the different requests. I didn't mention that in text, but they used in all of these scenarios 100 concurrent runs. And as you can see, by stress level 4, we need 1 container per request. So they are being balanced equitably, right? I mean, each one of the containers does only attend one of the requests. And this does make sense. I mean, as you get into higher stress levels, since the load balancing does work according to CPU, this distribution needs to be done. However, as you can see, again, it doesn't really relate to the host. I mean, it's not really impacted. Maybe because, I mean, this is like one assumption of mine. Maybe a user is limited into the amount of virtual machines or hosts that it can use. And you can go into AWS and say, hey, just give me more hosts, but we really don't know that. There are tons of like hidden limits in AWS. And also, well, they measured how the stress level affected the average runtime. Here, they are using this logarithm scale because otherwise it wouldn't fit. What did they find out? Well, I just mentioned, as higher stress level, there's more containers. Also, that the number of virtual machines do not appear to vary. And that level 1 to 9 average service execution time increased by a factor of 78. That's why you see this logarithm scale right here in this plot. How about provisioning variation? In this case, they did like a very different approach. They wanted instead to see how the number of containers in virtual machine was related to the service performance. This is the one that they report because this is like their strongest result, in which they have like a squared R very close to 1 that indicates like a very strong linear relationship. However, if you go through the text, they did another test which had a squared R of around 0.5, 0.6, which they don't really show the plots for. And for this, they figured out that the relationship was not that strong for the relationship between containers and average WAMP service execution time and the number of requests per hosts. Yeah, I mean, this one's kind of sketchy because they report this one with cold performance, but not with warm. So I don't know, maybe it would be nice to have that float around. For infrastructure retention, they basically started sending tons of requests, and between each set of requests, they start like spanning how much time was passing between each subsequent sets. Okay, so first they start sleeping by a very small time, then sleeping by a bigger time, and then sleeping by a bigger and a bigger and a bigger time, just keeping like an increasing backup. So as you can see, as the sleeping minutes increases, the percentage of containers that gets recycled increases too. This is expected. But what we really wanted to find out is when are all the containers and all the virtual machines recycled entirely, right? So after 10 minutes, 41.8 of the containers had to be recreated. And after 40 minutes, no containers or virtual machines were recycled from previous runs. And here they even go all the way and provide a suggestion, that is that they should, or whoever the cloud provider should increase the infrastructure retention when there is idle capacity. This is capacity in excess that is assigned to you, which we really don't know if it's assigned to you because it's serverless, but maybe it is. And this would help offset the performance costs of container initialization. Well, here one is just the same, but this is with the number of hosts. And as you can see, again, this is consistent. About after 40 minutes of sleeps, we all have new hosts. And also in the first case, because we didn't have hosts. For memory reservation, in this case, they started increasing the memory size of each of the lambdas, and they start measuring how much time it took for the request to come back. As you can see, for the cold runtime, it slowly gets better up to a certain point, and from the warm runtime, it tends to be like the same for all the cases. This is very interesting because this means that most of the runtime is being dropped in the framework. I mean, the framework, before it actually gets into the service, the code that is running, all the overhead is taking most of the time. This means that, in a sense, the memory stress or the stress level that they were setting up or how they wanted to measure this one was not working that fine, right? I mean, maybe they should have tried with different stress levels and to see if this really gets better, an edge with a memory increase by different stress levels. But, well, they didn't in this case. And what we can see around, well, they comment about like this unusual cases scenario in which there is this unusual use of additional virtual machines for 128 megabytes, which they say come from existing hosts from previous 1536 megabyte tests. But again, my question was, okay, if they were existing, why didn't you wait like for more time before actually running up this test again? But and they did some similar tests, but for Azure functions. And in these cases, as you can see around here, as the number of concurrent runs increases, so does the average execution time. We see a huge increase around here in the 50, this rapid increase, as you can see around here. And also they started measuring how many app service instances were used as the number of concurrent service requests increased. And they find out that there was 10% more, there was 10% more for this load of continuous 5 minutes testing and 90% more for continuous 10-minute testing. And well, that also they said that given additional time, some more apps instances coming and we have better performance. This is not something different to AWS or what it was stated. So, I mean, it's not worth like explaining these two charts that much. And yeah, so which are the big conclusions? There are many that are very related to numbers, but I like to think that these conclusions are like time constrained because tomorrow we will have very different results because how fast the cloud provider infrastructure and offerings are changing. But one of the parts that I really liked is that if you want optimal memory reservation size, you should perform benchmarking. I mean, it's not that the serverless will do everything for you. You need to understand whatever you are loading into the serverless infrastructure, perform some benchmarking onto memory, and then decide which is the right parameter that you need to choose. Because this is one of the few parameters that you can actually customize. So yeah, I mean, it's not that easy. And it goes in the sense of this one, right? If you start pinging your Lambda every 15 minutes, it will always be warmed, right? But this is basically a server with more steps. And yeah, well, that's basically it. Thank you so much.
I have a question.
Sure.
So from the previous presentation, well, it's questions, right? No. Time.
Yeah.
Can you go to the previous one? Yeah. Well, I have a lot of questions, but anyway. The first one is that from the Lambda functions to stay warm, how long can you keep a Lambda warm? Because I think that you cannot keep it forever and ever, right?
I have never reached that theoretical limit of like, okay, I will just ping my Lambda every 1 minute and just verify that it is always warm, and they never go through it in the paper. I mean, that would be really interesting, I guess, to go through. However, whenever I'm doing like serverless developments, I've seen that while I have never seen, for example, a timeout because of the Lambda being cold in HTTP. I mean, using like a standard HTTP parameters. So at least you can expect that even if it gets, even if you happen to get a cold Lambda, the request will go through, at least in terms of HTTP. But if you go into other places, there are some shortcuts, right? I mean, why don't you just return right around into the Lambda, and then inside the Lambda that is handling the request, you invoke another Lambda. And from the Lambda that is invoked, if you start getting close to the timeout, you invoke another Lambda. I mean, and you can just keep spinning and spinning and spinning. And that's what many of the event-driven offerings are using right now.
Yeah.
Yeah,
Well,
and just to add to that, huh?
The solution that you gave, it's quite simple.
Yeah, but just to add to that, in the third question that in the second question, I added a link. Some guys did this, like literally this ping the Lambda function to keep it warm. And apparently AWS completely arbitrarily at some point just like deprovisioned everything and just reprovisioned it again. So even this doesn't seem to be like a silver bullet solution to keep it alive. So yeah.
I mean, there you have it.
Cool. Do we have any more questions from the audience, or should we go to the discussion questions?
I have a, well, it's not a question, it's a comment. I had a kind of hard time trying to understand what is a microservice. And I don't remember if it was a reference or somewhere else, but I found that serverless and microservices are used to perform or to program chatbots. And well, it sounds logical to me after reading something else, because the chatbot is just sleeping until they have a request. And by my understanding, the customer are charged when the program is running. So joining all those things, I understand what serverless and microservices are kind of working. So I would like to know if you guys have another example of what can be programming or fit into cloud service, in the serverless computing with microservices besides a chatbot.
Well, I mean, I guess anything that's stateless and just responds to requests, like a web server that just serves content, could easily be done in serverless. I think serverless versus microservice is kind of like a separate distinction. Actually, I have a question about that. But yeah, I mean, my take would be anything that's stateless. Like if you get to one container or to the other, like you make one request, you get to one container, and then you make another one, and for some reason the load balancer just send you to another. For you, it should be completely the same. So it should be stateless, I guess. A chatbot maybe doesn't sound completely stateless, so maybe I'm not entirely correct. But yeah, I mean, I think serverless versus microservices kind of like orthogonal conversations, not really too related to each other. I mean, you could put a monolithic application that's not too big in a serverless, right? Like microservices is more related to an architecture pattern.
Okay. So I guess I will continue doing some extra research in order to understand the differences between serverless and microservice. But thanks a lot for your feedback.
Yeah, I mean, actually, my question, like the first question as a discussion lead, the paper talks about a microservice being a service whose code base is small. But then they kind of like walk back on that, and they start talking about microservices being an architecture, which is precisely what Rodrigo said and what AWS says. It's basically an architectural pattern, right? Like you have, let's think about Amazon. Like maybe Amazon has one service for catalog, but once you like click on thing, it has another service for the cart, and then it has another service to fetch your user information, and it has another service to fetch your history. So if they need, like, if one of those services is getting like a lot of heat right now, they can just spin more instances of that service, right? And part of, I mean, I don't know if there's a clear distinction, so that's kind of where the question goes. They tend to have like a very well-defined API that they expose to the rest of the world. So it's not like you make a library call, you make an API call probably through the network against that service. They tend to be I mean, they don't tend to be, they must be independently deployable. That's kind of what makes it as microservice. You can make them in different languages, right? Like you can have a microservice, like maybe the front end is built in JavaScript, but the back end makes more sense to be built in Rust. So they can talk because there's an API, right? Like probably like a RESTful API, they can talk. So it's like splitting your logic into smaller logical parts, right? That's what I think is a definition of a microservice. But the paper does talk about code size. So I don't know if we should discuss that. I think code size is irrelevant. The code could be huge, but as long as it has a clear API, a clear interface with the rest of the world, and it's independently deployable and scalable, I think that fits the bill. But I don't know what you guys think.
Yeah. So for me, like a serverless function, let's say, actually it's a microservice, because it's small, but a microservice can be full, like not like a serverless is something that you don't have to manage like the entire environment, for example, that you only create a function and okay, I want to execute it, boom. But that's part of, like, for example, it can be considered also a microservice, but a microservice, it can be also like a little program where you are managing, like, for example, you are creating your own container, you have your own environment that you are setting up things, but those like small things, like small operations, it handles the same type of request, let's say, and you can keep it alive, right? So it means more like about the duration of the time and how many and the resources that you are setting up, like that could be like the main distinguish, like, but like a serverless function can be, it's either way considered like a microservice. That's my understanding.
Yeah, I mean, just to reinforce, let's just imagine that we have a business and the only thing that the business does is that it allows you to log in and set up a catalog. Okay, Ricardo was saying. So we are expect to expose these two paths, logging and catalog. Set up a Docker image and I put it in a Lambda. Is this a microservice?
I would not call it a microservice.
Like, can you repeat it because I couldn't hear what you asked?
I mean,
it's breaking.
Okay. It's me, or are you hearing me okay?
Yeah, you were breaking up like for a second.
Just give me a second. I think I'm in the Wi-Fi extender. Just let me go back into the.
Yeah, it was a network issue.
Yeah. Just a sec.
Yeah, but Gautier, just to your point, serverless is more about the management of that code, and microservice, the way I understand it, is more of like an architectural principle.
Actually,
so they are.
I have a different approach that you have. I think the main difference between serverless and microservices is that serverless is our event. You need a trigger to launch a serverless function. And microservices are services that can be triggered by an event or can be running all the time, but they are separate, each one from another one. They can communicate via REST API with the other ones, but they are not the same one. I think in an easy way, that's the main difference between both of them.
Can you hear me? Can you hear me now? Or
Yep.
Yeah, we can hear you now.
Okay. Sorry. I mean, it also goes in that sense, but the example that I was showing along is what basically, just as I was saying, just imagine a business in which we only are devoted to login and catalog. You log in and you get access to the catalog. If I take this entire service, cramp it into a Docker image, and it fits in a Lambda, is this a microservice?
Yep.
Sounds like a microservices.
Maybe not. Maybe there's a logical separation between the login service and the catalog service. The login service deals with user authentication, with blah blah blah. Catalogs deals with databases. So maybe you have a bunch, like you need more catalog instances to talk with more database instances than you need login services. So
yeah,
you can also argue that it's the other way around.
You can have that, but that's a bad practice. That's something
so?
that you should not do.
What shouldn't you do?
Now
you need to have the services separate.
Yeah, you need to have them
separate. Yeah, services.
who says that you need to have them? That's literally the distinction, right? Like in a monolith, you have all of them in one thing. Like you spin your whole thing, and in microservices, you split them. That's precisely the difference.
That's a difference.
Yeah, here's right. I mean, if we were going like towards that code being deployed and being able to scale independently, then this would look a lot more like a microservice, right? I basically take the login part of the code that can be deployed independently into a Docker image and then send it to a Lambda. This looks a lot more like a microservice, right? But again, this may look like a monolithic if I start, for example, cramping a lot of stuff here in login. Because if, for example, at a given moment, hey, I want here sign up, but also I want here like the security. And then, I mean, it's like a never ending cycle, and you need to start always. I mean, the idea is that, or at least when you go through like the agile part of this thing, is that you start breaking whatever starts growing a lot into different modules. So, and not because, sometimes not because they are like, sometimes because this is the logic thing to do, and in some other times because you want them to scale differently, right? Why would you want to have a bigger, in this case, let's just imagine that I get tons of, I only have 3 users, but they go to the catalog every second. Why would I want this to be, why would I want the login section of it to grow? Because of the catalog growing, right? I mean, I don't want that. So what I would need to, if I break it in this way, then I can have the catalog growing independently and the login staying small.
Yep. And also, like, if you split it and you kind of adhere to what a microservice kind of should be, maybe the login is very front-endy and you do it in JavaScript, but then maybe the catalog is very system-C and you do it in C, right? And you have a, like, calling C code from JavaScript, I guess it's possible via, like, I don't know, like foreign function, whatever, FFI or whatever it's called. But it's kind of nasty, right? Like using a RESTful API might be cleaner. So there's that, right? Like maybe there's things that inherently belong in different levels of the abstraction stack. So that also kind of points to you at, yeah, these things should be split. Like it should not be one thing that we deploy.
And just to make a point here, Gautier, this is serverless because this Lambda, you are not managing it, right? So in this case, that is everything together, you are not managing this Lambda. But if I happen to instead deploy this service in a server and I need to take care of this server, and for example, if I need like a bigger service, take another server and just copy this code around into this server, then this is not serverless. So serverless goes in that I'm not managing this infrastructure, and server full or server aware is when you are managing this infrastructure. But I could perfectly just take this microservice and deploy it in a server full way, right? It doesn't have to be in a Lambda.
Okay, I would ask this question in the in the back or in a different way. Can you run microservices in a different environment than serverless? I mean, can you run? Yeah, you can run you can run microservices in a infrastructure as a service or platform as a service.
Yeah, you can run microservices in your computer. Like if you have 10 different services and each listens in a different port, they can all talk to localhost, column, whatever your port is, and they're running in your computer, right? Like
okay. Thanks a lot, guys. Thanks a lot for your feedback. I understand better what the difference and the coincidences between the serverless and the microservices. Thanks a lot.
Cool. So yeah, so that was question 1. So I guess we are settling on the fact that it's not really about code size, but more like an architectural principle, right? So I guess that's the answer we got here. That was my most interesting questions. The one with more discussion. The other one is the paper clearly shows that WARM setups have way better performance, and that link I sent earlier, which is in the spreadsheet. What Rodrigo said in the last slide, by the way, had tip to the Rick and Morty reference. yeah, like keeping it warm, right? Like you want to keep it warm. So should cloud providers charge a premium to keep like to ask you, hey, do you want me to keep these like warm up to like some SLA level? Should they like, is there a business incentive for them to do so? Is there a business incentive for customers to do so? Or maybe these hacky, like, let me ping you every 15 minutes is better approach? Because I mean, arguably this is exactly what's happening, right? Like this is just server full with more steps, right? So as a customer, it's like, hey, I want like blazing fast performance. Let me just pay you to make sure that they are warm because I know of there's better performance. So do you guys think there's a business here, a business opportunity? The paper actually mentions they don't, AWS doesn't support parentheses yet paying for ensuring that your thing will be warm. So do you guys, what do you guys think?
Well, it depends. I don't know what is the cost for AWS for the provider to get that. Like this can be a hack, and this is a hack that maybe in the future can be avoided, or can be blocked. I don't know, because I don't know what is the cost that the provider is getting for keeping warm an application or a container. We need to know the cost for them. Maybe it's cheaper for them to keep it like that, or maybe it's something that they are aware of, but they don't have still a way for avoiding that.
I honestly don't know. Maybe there is a business opportunity, right? Like if you want your thing to be serverless and blazing fast, is like, yeah, your request will not cost you like 20 cents every million. They will cost you $1 every million, but sure, they will be fast.
Yeah,
right?
but
like, I don't know.
but this is like doing a reservation for something, right? Like getting something like forever there.
Yeah, this could be something like platform as a service, right? Not function as a service, not Lambda.
Yep.
Then you can go probably best with that approach instead of just keep it warm forever.
Yeah.
Yeah, probably. I mean, in those scenarios. I mean, but I mean, being honest, right here, if any of the three does it, it will find a way to convince you into growing into it, right? I mean, let's say that, okay, I have found a way to always keep them warm that is cost effective for me, Amazon, Azure, or Google. I will find a way to promote it to you, and even will create some way of architecture of saying, hey, this is warm serverless, right? I mean, they may end up with it, but only if they manage to pull it up with them keeping the box, right?
Maybe that kind of approach can affect the elasticity, because they're keeping occupied some resources, and it's not business for them. I know for a fact that having a system in idle state and another one in like running some application consumes 3 or 4 times the power of compared to an idle system. So maybe it's not something that they want to avoid, that kind of scenarios to have the environment warm.
Fair enough. Yeah, maybe the business lies in, yeah, I mean, I'm not making any promises about performance, so up to you if you use serverless, but I'm gonna squeeze the hell out of my servers and put as many containers from as many customers as I can, and then kick them out as soon as possible and just put more containers in. So yeah, maybe there is no business for them to do it. But if people are doing this, ping me every 15 minutes to keep it warm, maybe they are kind of like getting this scenario where they are not evicting containers. They are essentially idle, right? It's just a ping every 15 minutes. So they're not evicting them. They're not putting new containers in this machine, and yet they're not charging you, right? so maybe there is something to be gained by them, but I don't know. Cool. So yeah, if we don't have any more questions, I guess we can go to the next presentation.
Okay, thank you guys. Thank you, Rodrigo, for a great presentation and the reference. That's a great episode. You should watch it. Thanks, Ricardo, and everyone else for joining this discussion. So I don't know, you guys want a 5-minute break or shall we continue?
I would say I continue.
Yeah, let's power through.
Okay, let's keep it warm. Okay, let's go. So Paul, you can.
Yeah. There is like a warning sign when I click and share.
Why
That's,
you cannot?
that's interesting. That's give me a second. I need to open preferences, security, and privacy.
Or should I open
Give me a second. Yeah, probably I will have to close it probably. Let me see.
Okay. Just something about Ricardo's comment about basically talking about microservices and the size and the functionality. I mean, they would be some like not exactly the same thing, but I mean, you can see that there is a relationship between size and the functionality. You know what I mean? I mean, the bigger it gets, you're having more, or you don't see it like that?
It also depends on your skill, right? I mean, there are people that need like 200 lines of code to get something working, and there are people that need one. So, I mean,
one.
Yeah, I mean, if you extend it to some extent, it can be seen. I mean, it can have certain relationship. So, I mean, maybe that's why the authors are basically referring to that.
Yeah, but I think it's more related to the coherency, like in the example, the login is inherently very different from a catalog service, right? So even if they're both 1,000,000 lines or 10 lines, they both belong in separate realms, right? In separate services. Like, so it's more about where you draw the line, and like once you have your service, it can grow. Maybe it organically grows, and eventually maybe you split it, right? Like maybe once it grows, it's like, okay, you know what? Like within login, there is a part about all the authentication with all the IDP and SAML and blah, 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 and the actual part of what we want to do, right? So maybe you can split it again. But I don't think code size is a good measure because it's so subjective, so unreliable.
Yeah,
like,
I agree.
I mean, 2 lines of Python are 100 lines of C, right? So, so it's, yeah.
Yeah, true. Okay, yeah, go ahead. Go ahead, Paul.
Yeah. So can you see my screen? Because I don't know how to use Zoom.
Yeah, we can see your screen.
Yeah, we can see.
It's just, yeah.
Okay. So, well, this is going to be short because it was only 5 pages and actually it was a really small topic. So, well, I hope it's short. Sorry. So the topic, it's Agile Cold Starts for Scalable Serverless. Give me a second. I don't know how to come back. Sorry. I'm really bad with this. So Agile Cold Starts for Scalable Serverless. That's the topic of the paper. And well, I only wanted like to give a reminder of what a serverless or function as a service is. That it's like packaged code with some dependencies, like for example, the beans and leaves that live together for a just-in-time dispatch. Like when I said just-in-time dispatch is like by request, right? So you invoke you make a call or you invoke the function and then it's executed. And usually it's used to perform quick executions. So before, as well, it was mentioned in several of the presentations, you had to load, like, for example, virtual machines that contains also, like, for example, different operating systems and things like that. And then on top of that, you load all the libraries and all the applications. So now instead of having all the virtual machines, you have like an engine, like let's say a the Docker engine, for example, and you are executing containers at the top. So this is only as a reminder because it's important for the paper. And another thing that also was mentioned in the previous presentation, it's about the cold starts and the warm starts. And the paper also mentioned the pre-warm. one. So the cold start is a container that is started from scratch. Usually, well, this can happen, like, for example, the first time that it happens the first time that you execute, like, for example, a Lambda function that you have to initialize all the containers. And you have to load, for example, the container, and then you can launch the container after everything is initialized. Then the pre-warmed start, it saves the cost of launching a new container because it pre-creates the container with all the needed code, for example, Ubuntu image or whatever. And then it starts it when it is in boot. And the warm states, well, it's like after the pre-warmed start that it saves the startup time by caching like the running, well, a copy of the running code container or code in the environment, and it can be executed fast. I will do an analogy on the distinction of these three in a while. And for example, when you call a Lambda function or a serverless function, actually, it doesn't have to be a Lambda. What it happens is first that you download and extract the code of the container, and that's part of the cold start. And then you start setting up all the environment and resources for that container that it's part of the creation. And those two steps, it's mainly a part of the cold start. Then when the container starts, if the container is started, then we say that it's in a pre-warm state. But once at least one time the code was executed, it's now considered the warm state. And then, well, you have the opposite, the removing the containers and things like that, but we're not talking about that topic here right now. So I will do the hot dog analogy about the cold, pre-warm, and warm states, where like we are talking about a guy that is selling hot dogs, and the functionality or the goal, that is the code execution part, is to deliver hot dogs. Okay. So the hot dog analogy actually for explaining the cold and pre-warm and warm states are that when you are downloading and extracting the code is similar as if you are buying all the ingredients. For example, you are going to be selling hot dogs, then you need to go and purchase all the elements, bring them home or to your store, and then extract them. So that's the first part. Then the next one, also part of the cold start, is that you have to warm up your iron, right? Because where you are going to make the hot dogs or hamburgers or whatever, and you are going to prepare all the resources that you are going to need so you can deliver the hot dogs. So that's part of the cold start. Then the pre-warm state would be you start warming up your ingredients or preparing, like chopping all your ingredients or preparing everything. So everything is already ready. So and done. So when you sell like a hot dog. And the last part is like in the warm state is, for example, when you have all the hot dogs already prepared and then you are ready to deliver. So if a customer comes and they ask a specific type of hot dog, because there can be different type of hot dogs, right? You can deliver exactly the hot dog that they want. This is super similar as what, for example, McDonald's makes, that they prepare different type of hamburgers, for example, and then you can start, well, you request a hamburger and it's already prepared, right? Because they are already warmed. And in the pre-warm state, you don't know actually what are you going to execute at that moment, you know.
So basically, going to buying a hot dog is going to container to a pre-warm, and creating the hot dogs from start is the cold one, right?
Yes, exactly. So as I mentioned in the beginning, the functionality is to deliver the hot dogs, right? Not the preparation.
Yeah.
So yeah. So as I mentioned, we start like purchasing all the things, extracting the elements. We warm the iron and we prepare the elements. That's part of the cold start. that it's similar to the ones with what a container is. In this case, your iron is your container, or you can say like, or also like sometimes kind of virtual machine, let's say, that if you have so many requests, you have to start more, right? You have to get more irons at that moment. And then when you want to pre-warm, you start heating like everything, right? Before you start mixing all the condiments. And then if you have everything, you prepared everything, you can start selling them, right? So if somebody comes and you are in a pre-warm state, what you have to do, like they ask for a hot dog, they will, you will prepare the hot dog and then you can deliver it, right? Does it make sense?
Yeah.
So this is the hot dog analogy on that. And something that I have to mention as well is that about the warming up, you know, similar to the, what's the name, in the functions. Well, Lambda, for example, keeps a container alive between 30 and 45 minutes usually. That's why Rodrigo, it's his name, I think, he was saying that to keep alive the container, he's sending a ping or calling the function every 15 minutes, right? Like that's what he does. So that's something called periodic warming, that it consists on submitting dummy requests every so often to induce the cloud service provider to keep the containers warmed. And it's similar in the hot dogs, right? If you are not having customers, you're not going to keep the iron on, right? You're going to turn it off at one moment. So on the paper, they also mention about, well, one of the main goals on the paper, after like we have this distinguish about the warm, pre-warm, and cold starts. It's about the time that it takes on the cold starts. And the cold starts usually takes a lot of time, as Rodrigo showed in some of his graphs. I will show it in a while in other graphs. But one of the things that takes the most, that consumes the most time, are having cold starts. So what this paper tries to solve is to reduce the time of the cold starts. And how do they do this? Is by using post-container pool well, something called a post-container pool manager. They call it like that. That what it does is that it creates beforehand some networks and network connections and things like that. So this was when the study was done, they realized that one of the things that consumes the most time when initializing a container is the network connections. So instead of doing that on the cold start, they are leveraging, I don't know the word, the, how you say, the network creation and the network connection to a different system. So as it says, like in the paper, it says are pre-creating networks and connecting them to function containers, so that the time spent in the network create and in the network connect steps are removed from the critical step of the startup. The startup is on the cold start. And here there are some diagrams about that. Like, for example, you invoke the system, and on the start, that's why I don't want to move the mouse. You create the container, and then the container, before you can even execute the function, or before the function is executed, it tries to create the network, an internal network, and it creates a network and it tries to connect internally. And then when everything is ready, then you can start launching the container, that it loads, like, for example, the function, and then it executes the function. And after the function it ends, then there is a cleanup state that it will kill it will send a signal to kill the container. The container will die, and everything, all the resources will be how you say, free. So in the post-container pool management, what it happens is that instead of creating all these, that these are like the steps that takes the longest, what it happens is that it triggers it makes a call, and on the cold startup, it creates the container. And then since the network is already created, it will request only one of those network connections, and it will attach it to the current container. And then the container can start and can be executed. And then, well, it happens the opposite, but instead of disconnecting the network, it will only release the connection to the same pool manager. There is another diagram about this, like for example, here, that it's that, like for example, the pool manager at the beginning, it will start everything. It has, like for example, an amount of containers that were initialized already and have a network created each one, and they are connected as well between each other. And then what happens is that when you want to call a function, the function, how you say, to the function is assigned one of those POS containers. Well, actually one of those, how you say, networks. So the execution will be executed, but it will save the time of the, it will use these POS container resources, that is the network. And then when the function ends, the function dies, but the network connection is still alive and it can be reused. So it's like similar to threads, that you are running several threads, but you can keep in sleep state the threads, right? So the analogy also with the hot dog analogy, including it. So it comes in step 2. So it's that when you are making the startup and you are heating or pre-warming the iron, you have also, like for example, you have your environment that is the iron, and you have your resources, right, that are all the ingredients of your hot dog. In this case, the ingredients, it's the analogy of the network. So instead of doing that, what it happens is that you remove the loading the resources, but what it happens is that the resources are already loaded and available at any time of the life cycle. So it's so that way, instead of if you, for example, want to deliver a hot dog and and the first client comes in and you are going to warm the iron, you don't care, you don't have to spend time like preparing everything because it's already there. So about this, again, like for example, the study shows that they were making some tests using OpenWhisk, that Apache OpenWhisk, that it was mentioned in a previous presentation. And they found out that the latency of the cold starts, well, it's really high, and usually because of the network connections. And they were measuring how long it takes, for example, on the startup time, on the runtime. Startup time is the cold start, and the runtime is the execution after it's like in a warm state. So how long it takes to execute 1, 10, 20, 50, 80, and 100 functions, where they were creating, I think, prime numbers only. So they were not requesting any connection to any database, nothing like that. So they were creating only prime numbers. And as you can see, most of there is a significant part, well, time that is spent only on the startup time. Actually, it's more than the 90%, especially on the when you launch 100 functions. Also on this graph, you can see, like, for example, how you say, a similar, well, in a different way, that most of the execution time is on the startup, and the other it's actually on the cleanup, but that's only mentioned on the conclusions right now. We can discuss that later. So after you use the what's the name, the POS container pool management, that, as I mentioned, is that in a different application, let's say, you are creating a pool of containers that only creates networks. So when you launch your Lambda, well, your serverless function, then you have only to touch the network. You can see the comparison of the previous time and the new time. So it's reduced around the 80% of the, well, it saves you around the 80% of the time if you use this type of logic that they applied. And this is also another representation of that. And now you can see that the thing that takes the most is the invocation time. Then, well, this was a table that was shown there that I think that actually pre-warm and warm should be the how you say, the other side, well, the other flipped, because like it only shows that in the call functions, you have an environment dependency. Like, for example, you depend on warming up, like, for example, the iron, and you have function dependency because you don't know what type of hot dogs you want to sell, for example, but there is no memory usage. And also it takes a lot of time to achieve your goal or the execution, that it's like, for example, 20 seconds for 50 functions, but it consumes low resources, but it takes a lot of time. So on the pre-warm, similarly, like you see that you consume more resources, but it's less time. Then the warm one, it consumes more resources and less time. And with the PCPM, how you say, you don't use that many resources, but the time it's like not an average, but it's in between like the worst scenario and the best scenario, right? So this is probably a good balance between the trade-off of how long you want, like how fast you want the functions to be executed, and the total of memory that you are going to be using. So something that I want to mention is also that, as we mentioned, that sometimes you want to keep, like, for example, a container alive so you can execute it fast. So that part has also, how you say, what's the name? What's the word? Well, it has a cost, right? And the cost usually it's a memory usage or more resources usage, right? So that's why they were this paper actually was introduced, because they wanted to look how you say, something that benefits you on the performance, but it doesn't increase the resources, or it doesn't cost you that much. So that's all. The paper was really small. I'm sorry, guys. I don't know if anybody has questions.
I envy you. Mine was 42 pages.
Mine was 5 pages.
I think that in the future this could be improved by, for example, having intermediate states or and abroad options of warming up things.
Like warming up things.
Yeah, for example, let's put that the example of the hot dogs.
Yes.
It is different to have the iron cold or warm. That is like obvious steps to take, but one could be, for example, having the right tools reachable, and not having them. You can spend some time looking for the tools, or in saving some time if you already have them there. I don't know if, for example, that could be in the same way some services or from
like customizable warm, right?
Yeah.
I mean, what you to get quicker?
Yeah, we have, for example, in computers, we have the hibernation or restart or turn off your computer. It depends of the different power stages, but between them there are like 5 or 6 power states between them, and they have like Rodrigo said, customizable scenarios that you can pre-site or prevent in order to provide a better service at the end.
Yeah, And actually, like for example, something that I was thinking about this paper is that they are only focusing on the networking part. But actually, I think that there are other cases, like for example, when you are trying to do other stuff, like for example, connecting to some external hard drive disk, even when it's part of the networking, but you want to connect to other type of resources. They are talking right now, they are measuring this part, right? And you can have other managers for other type of resources, right? That's probably not the only one.
And also regarding this, I think cloud service providers are aware of about the most with the most traffic times, and against the times that there are not too much traffic in order to prevent. So it's interesting how they can manage and control the traffic and also the requests from customers.
Yes. So about like the request from customers, actually, this brought me like something that I remember. I don't know, you guys, like for example, when do you think that it's good to use, for example, this type of managers, the pool managers, and when it's better not to use it? Like for example, I don't know if you have an example of that.
Paul, it's
okay. I'm sorry.
I was doing to do that question.
Oops.
Okay, anybody else have another question? Because I have one for you. Okay, my question is like, in which cases or what type of applications do you think that it's better to use like warm or pre-warm, or maybe use the Pause Container Pool Manager? Like, yes, that's the question. Can you give me like some examples?
Yeah, I do have one, but I don't know if others first have an example.
Okay, if nobody.
Okay, so something that I know by experience is that, like for example, a lot of companies are moving to serverless, right? But serverless, you don't have to use it only for, let's say, user on-demand requests. Like for example, here in the hot dogs that you are saying like, okay, there is one client that it's coming, that, well, a real client, let's say, and they are purchasing a hot dog, right? You can use microservices, for example, for nightly jobs, right? Or cron jobs, that it's how I call it usually, that are scheduled jobs that triggers at night. For example, calculating the salary of one person from a company, you know? So what happens is that, okay, during the day, some things are happening and you say like, okay, it's midnight, I'm going to execute a cron job, and this cron job will trigger one Lambda function for calculating the salary of each individual. So there is one Lambda function per individual. So in this case, for example, since the user is not waiting and the waiting time is probably less expensive, the computation time, than having a pool manager system always there. So probably this is a case where you don't care if it's a cold system, unless there are so many users that you have to calculate the salary that it takes longer than you want, right? Also because it's more expensive to manage, for example, updates or any type of updates on the manager, and also it's developer time and more microservices to handle. I don't know what you think, guys, about that example.
I think the warm, it's better when you have like a dependencies, like the output of your serverless is going to going into another application. So if you have call, your other application needs to wait until until everything is warm and then executed, and you will add everything to the pipeline. And call it's better when you can run in parallel a lot of function at the same time, and you are not waiting like for an output or something like that.
What do you think about like calling these unpredictable requests, that you don't know how many unpredictable requests and number of requests you're going to get? Because that's one. It's like a hybrid between your solution and my solution. Well, my idea, and how you say that. For example, if you don't know when the functions are going to be executed, or they are called by other functions, and you don't know how many times and things like that, I think that probably it's better to do this. But if, for example, if you have control on what is happening and at what moment, probably, and you can calculate, for example, how long it will take something that is more predictive, probably a cold start, it's okay to have, depending if it's on the range that you want, on all the metrics that you want. I don't know if it makes sense.
I'm pretty sure that they already have studied these kind of scenarios.
Actually,
for example, we can know in the streets what are the time slots that there are more cars in the street and others that they aren't. So and they have these whole resources. I'm pretty sure that they already have studies about it.
Actually, that's a good topic that I like a lot, because that's about predictive and also preventive, right? So this type of, how you say, what you're mentioning, I think that it's more related to predictive behavior, and what they are doing with the PCPM, it's a preventive, right? So what you have is that you are loading so many networks that are always available, because actually in the paper it mentions that you can load up to 1024, because that's the limit from Unix and blah, blah, blah. But either way, since they are not that costly, they try to load as many containers as possible to create as many networks as possible. And so when there is something ready, when you need it, right? That's something similar to what ECS does, right? The elastic, what's the word of ECS? I forgot. So it's the ECS is a system that manages different type of, let's say, machines. You know that when you have more requests, it launches another machine, right? But a lot of times, to be able to handle this, what you do is that even when you are using only one machine, you have one or two available at least. So when you have more requests, you start using the new ones, and then other ones start, how you say, booting, while the others are handling your requests, right? This is also something similar to what Kubernetes does, that Rodrigo mentioned in his presentation.
Okay, I have another question. For example, you are talking about all the good things about the Faust Container Pool Manager, but someone of you think about the disadvantages of this? Because the paper don't mention anything about disadvantages, but what do you think about, like, which are these disadvantages? You have any idea? No? Okay.
I was just when I feel that many of these strategies are kind of seeking a way to hack into a system, right?
Yeah.
I mean, I see that. I mean, there are many places where you see these ones, right? I mean, but I do feel that many of these strategies are like a little flaky. I mean, in that the service providers, they don't care of what we are doing on our end. So they can do any change, and that change may basically break our entire optimization scheme like completely. And it's okay, because we didn't agree never that they would host our strategy or they will protect it in any way. I mean, that's what I feel a lot in many of these cases. It's like we're having like a very official blog of ways to hack AWS, like in real papers, but I don't know. I mean, I feel that whenever they do an important change or a breaking change, they will just break this apart.
Yeah, I agree with you. This all kind of stuff sounds like a hack that people are doing over the providers, but I mean, it's obvious that the providers know what is happening right now, and there is a reason why they are not doing this officially. So that's the possibility that you said, that they don't have the infrastructure for doing that, or maybe it is expensive for them to make it officially, or it is hard to prevent this, so, and they are still trying to do it. But yeah, that's what you said.
But why don't you see this type of ideas as basically ideas for providers, not for the users? Except exactly like this paper, except killing the container, just keep it in PCPM mode, you know?
Because
Yeah,
at the end, those are resources that are still using, right?
Yeah, but the idea, I mean, if you go to the table, the final table, that you're comparing the results, you see basically what you're sacrificing is just 2 megabyte of memory. That was the thing.
Yeah, but that is in our site, right? What is the site, the Amazon sites or cloud sites or provider sites? What they are sacrificing when you are doing this?
Yeah, I mean, it's not like it's only like terms of, it's not only numbers, right? It's not like, okay, we're getting very memory or very CPU, or you get this much, but also like, okay, how are people? What is the size of the team that I need to keep up this container thing running, and for it monitoring and to verify that it's working okay?
Yeah.
I mean, for them, it's, if we can many of these papers are like in the good sense, right? Yeah, they are for the providers, but I mean, in my workplace, at least, we have seen like 10 different ways to hack through the Lambdas. I mean, and many of the times AWS just, hey, breaking change, and our way to keep it warm just.
Yeah, and actually recently, not only on that, recently it was realized, like for example, in a JavaScript log system, there was a way to hack it, you know, by introducing some logs with code execution.
Yeah, the
log4j.
Yeah, but apart talking from this also, as the other people were mentioning, this is, for example, how you say, some metrics, right, that we can measure. But what happened with the things that we cannot measure, like for example, security? Well, we can measure security by doing some benchmarking probably, but let's say that we cannot measure it. The security, there are some problems, for example, with network security, because you are also, for example, creating some network IPs from the beginning. So you are probably opening ports and things like that. And then when you are assigning into containers and reusing network connections, you can have problems, right? Security problems. Also business logic problems, probably. So those could be, like, for example, some disadvantages of the PCPM. And as we mentioned before, like, you don't know what it costs behind, right? You don't know if developer time, like updating things, etc. A lot of things. So we don't have to see only the compute and the memory costs.
Yeah, I think this is a point of view from the user, but we are not seeing the point of view of the provider.
Yeah, if it's from the provider, I'm happy.
Yeah, true. At the end, I mean, the problem is oversimplified. You're right in this type of paper. And at the end, it's a trade-off. You're sacrificing something to, you know, certain benefits. So there was really good ideas. Like if that basically if that can be customizable, maybe, I mean, you remember it was last week we were talking about optimization, right? So maybe, I mean, that can be related to this. If you can do that really, I mean, make it customizable, but in a very dynamic manner, based on exactly what type of basically containers you have, then that can be something interesting, you know. I mean, to find a bottleneck and try to customize that for any container automatically.
Yeah. But either way, like I think that, for example, with since this paper was done like from people from Google and things like that, probably they are solving or have solved these type of things internally as well, right? One, to be competitive and provide better services, but not only that, that a lot of times, for example, Google and Amazon do it internally first for their own sake, and then when they are old libraries, 2 years old, let's say, they release it right to the public.
Yeah, that's real things. I mean, and then what we're thinking and we're discussing is based on publicly available information. There should be a lot ongoing there that we are not aware of. That's true.
Yeah. So I don't know if anybody has more questions or other topic related to this.
No.
No.
Okay. Thanks, Paul. Or I mean, you made everyone hungry with that hot dog stand. So
well, I remember that there was a restaurant analogy, but I was trying to find it out. So I was like, well, the restaurant is similar to the hot dog. So
that was a good one. That was a good one. Thanks, Paul. Thanks everyone for today's presentation and discussion. So just remember, next week we don't have paper presentation, but we have those deep dives. So again, what we're going to have is like something equal, not like we're going to have 4 groups. So probably 20 minutes presentation from each group, hopefully with participation of all the group members, you know, in the presentation, and also discussion that we're going to have. So that's it. I mean, see you guys next week. If there is no more question or comment or doubt.
I have one question for next week presentations. Are there any special requests or a normal presentation?
No, just normal, just participating all. I mean, basically not just one person doing it for everyone, but everyone helping each other and presenting.
Okay, thank you.
Okay.
Thank you.
Yeah, I mean, if you don't have each other's contact, now is the time to exchange your email address. I mean, if you're in one group, so you can communicate with each other. Okay. All good?
Okay.
Okay. Have a good evening, everyone.
Bye.
Bye. See you next week.
Bye.
Bye.
Thank you.
Bye. Thank you.
Pedro, what's your email?